Hi everyone, welcome to my thesis presentation. First, I would like to thank the opponent for that excellent presentation, which saves me a lot of trouble introducing the field. Instead, I will focus on going through what has been the work I've done the last 4 to 5 years under the umbrella of sodium-ion batteries. I will go through this in 4 distinct sections. First, a brief introduction, where I will show my view on sodium-ion batteries and how that has motivated my work. And then we'll go into SI and anodes, which has been the focus of papers 1, 2, and 3. Following the anodes, we'll go to the other electrode, the Prussian white cathodes, which was the focus of paper 4. And last but not least, it's the electrolyte work that has been done in papers 5, 6, and 7. So, as you all know by this point, batteries are energy storage and conversion machines or systems, meaning that they take electrical energy and store them as chemical energy and do the opposite conversion when you need to use energy. Batteries comes in all sizes and shapes, moving from microscopic to humongous batteries, and they all have basically the same criterion for evaluation. How much energy can they store? How much power, i.e. how quickly can you charge and discharge a battery? How durable are they? Meaning how many cycles do they last? And are they safe? Are they costly or cheap? Now, depending what you want to prioritize for this criteria is very much dependent on the size of your battery. For a small battery for microelectronics, volumetric energy density might be your main concern. And for a mobile phone battery, this is true. And they don't care that much about the cost because it's used for a very cost intensive product. A mobile phone costs a lot, so it's worth spending a lot on the battery. When you move up to something in the size of an electric car, you start worrying more about the cost and also about the safety, because you have to have people riding on the battery, more or less. And also the battery constitutes a significant part of the cost of the electric car. However, since it's a mobile application, you still want high energy, and that means that car batteries have a lot of demands on them. If we move up one further tick on the scale to the grid storage applications and batteries for, let's say, boats or really large applications, then you start looking more and more at the price, because here energy density does not matter as much. Instead, you're looking at cost per kilowatt hour and cost per kilowatt hour per lifetime. So you start looking at how many cycles can I use this battery for how many years, and what did it cost at the end. However, energy density does play a part of the cost equation as well, so it's rather complex. But if we look at how a battery works, it doesn't matter if it's a large battery or a small battery. This is the typical setup you would see in a sodium-ion or lithium-ion battery. You have 4 principal components, starting with the current collectors, which enables the electrons to go to the external circuit where we harvest the energy. After that, you have the heart of the battery, that is the electrodes. The electrodes are split into 2 different types, the anode and the cathode, which is the negative and positive electrode. And these in turn consist of 3 different types of components, the active material, the binder, and the conductive additive. Now, in order to move alkali ions between the anode and cathode, you need something that we call the electrolyte. In this work, the electrolyte is completely consisting of liquids, although there are alternatives. But you can say that an electrolyte consists of a salt and a solvent, which enables ionic transport. However, since the electrolyte is a liquid, we need something else between the electrodes so they don't touch each other and short circuit, meaning that we can send electrons straight from the anode to the cathode. To prevent this, we use a separator, which is a porous membrane that allows ions through, but not electrons. It's usually something that looks like paper with micropores, which enables wetting, but still electrical insulation. So the first point in this introduction should have been, why do we do sodium-ion batteries? Why not stick to lithium-ion batteries, which are the state-of-the-art batteries right now with the best performance by many metrics? Well, the main reason is the abundance of sodium. Sodium exists in the Earth's upper crust to levels of 2.6%, while the equivalent number for lithium is 22 ppm. Furthermore, lithium is mostly found in concentrations in certain distinct regions of the world, which means that not every country has the same access to lithium. However, there are of course some downsides with using sodium, such as the higher reduction potential. And a higher reduction potential of sodium means that we typically get lower voltages than lithium-ion batteries. But this difference is only 0.3 volts, so that's basically smaller than the difference between different lithium chemistries would be. However, one important thing is the larger ionic radius of sodium as compared to lithium, and this is a troublesome attribute, which means we have access to less electrode materials. When we're dealing with electrodes that intercalate ions, the larger size of the sodium ion will hinder things like diffusion and give lower capacity or higher volume expansion. However, this is the typical answer to why we would need sodium. In my view, the abundance of sodium is not enough to motivate switching completely to sodium-ion batteries. In fact, the cost of a battery nowadays is very little depending on the lithium price. Most of the cost in a battery comes from the cathode materials. In lithium-ion batteries, they use cobalt, nickel, sometimes vanadium, a lot of manganese as well. And if you want to substitute lithium for sodium while using the same cathode materials, then you will basically make very little cost savings. In fact, you might actually end up losing money because you get less capacity and a lower voltage. Instead, if you want to leverage the abundance of sodium, you need to keep all the materials in your cell abundant. And one upside with using sodium ions is that they do not alloy with lithium at low potentials, which means the current collector on the anode side, which is copper in the case of lithium, can be substituted for aluminium. However, looking at the cathode materials, we could use the same materials as lithium, but in my view, it makes little sense to use sodium-ion batteries unless you use something that's truly abundant, like iron or perhaps even manganese. But in my opinion, if your whole cell isn't cheap, then switching to sodium makes little sense. That being said, let's have a closer look at the anodes in sodium-ion batteries, or in batteries in general, and let's have a look at what we call the solid electrolyte interface. This is the focus of papers 1, 2, and 3, and they will make little sense unless you understand the SAI. Now, the SAI is a component that I wish we wouldn't need. It's basically an effect of our electrolytes having insufficient electrochemical stability at reducing potentials. So when we use our anodes, we try to keep them at as low as a voltage as possible to gain the maximum potential of the battery. However, that means that we're slipping outside the electrochemical stability window of the electrolyte, which means the electrolyte will react on the anode, it will reduce. Fortunately, lithium-ion batteries solve this issue by making the reduction products being good passivation layers that prevented further reactions. And we want to emulate that with sodium. So we want an electrolyte that breaks down, forms an electron barrier to stop further reduction from happening, but also that keeps the ability to pass sodium ions to and through the anode, so it must be ionically conductive. Furthermore, this breakdown on the electrolyte, it costs us both solvent salt and sodium inventory, so we want to form as little as possible of this SAI. We want it thin and we want it stable, so you only have to form it once. And this is the starting point for the work of paper 1. In paper 1, we actually showed that sodium-ion batteries have more troublesome environments than lithium-ion batteries. We showed that pausing a cell at full sodiation and a lithium cell at full lithiation does not yield the same type of self-discharge or parasitic reactions. I did comparative testing with several different systems, including 2 lithium systems and 3 sodium systems. And it was quite an easy test protocol, but that allowed us to show that 1, sodium ions do have more self-discharge than lithium-ion batteries. 2, it's not dependent on the high reduction potential of sodium. And 3, additives and surface area are definitely factors in this process. However, self-discharge is one thing to prove. We wanted to see if the SAI was soluble. So there was a debate at the time, since sodium salts are typically more soluble in water than lithium salts. People speculated that sodium SAI products would be more soluble in the electrolyte. And there are many mechanisms that lead to self-discharge, but by using XPS, I could show that the SAI during a pulse is actually shrinking. And this shrinkage of the SAI actually gives quite strong support for the hypothesis that the SAI is indeed dissolving. So that was the starting off point, and I should say this was done in standard carbonate electrolytes using hexafluorophosphate salts. But it wasn't done in a practical system. So in paper 2, we took a look at tin phosphide. And here I synthesized tin phosphide, which is a compound with tin and phosphorus. It has a good capacity, a decent voltage, but quite complex behavior during cycling. For example, it converts to metallic tin and phosphorus during the first discharge. This was known at the time I did this work, but I wanted to prove that this is indeed the case before studying it further. And this was done by combining powder XRD and operando XRD. As you can see in the 2 pictures on top, you can see the characteristic peaks of tin phosphide, which are represented here in the red square, actually disappear during the first sodiation, and they do not reappear. So this is important because we're actually cycling tin and phosphorus, not tin phosphide. We're just making a good mixture by putting it in this compound form. Another important thing to know about tin phosphide is that the capacity retention is quite decent for a number of cycles, and then it drops off abruptly. In paper 2, took a look at the SAI to see if that was actually functional. We used X-ray photon electron spectroscopy to characterize this, and did this at different states of charge. And by measuring several samples at different sodiations during the first states of sodiation during the first 1.5 cycles, we could show that the SAI was actually becoming thick, thin, and thick again. We could also show that the composition within the SAI actually changed. So this SAI is much more dynamic than we would like it to be. Now this is somewhat complicated by the volume expansion that tin phosphide undergoes, I should say tin and phosphorus, during sodiation and desodiation. And we wanted to look a bit more at this. So in paper 3, we looked into the electrochemistry. We did some cyclic voltammograms, and we knew from this that the electrochemical reactions that we wanted to study occurred below 1 volts. And in paper 2, we charged to 2 volts. While in paper 3, we changed this and took 1 high cutoff potential and 1 low cutoff potential to see if we could see any difference. We performed much the same study as in paper 2, but we used 2 different salts and this different cycling protocol. And indeed, when we lowered the upper cutoff limit, we got much more durability out of these cells. Literature at the time was indicating it was agglomeration of tin that would eventually kill the cycling in tin phosphide. And by combining these 2 cycling protocols with XPS, I could show that indeed the tin is actually becoming a lot more exposed if we charge to 2.5 volts as compared to 1.2 volts. So it seems like we are actually stripping the SI of the tin particles, and that helps them meet each other and fuse together, and that will inactivate a large portion of the tin, and this is the cause for the abrupt decline in capacity. I also showed that sodium FSI is preferable to sodium PF6 when you cycle the system in half cells, but the main point here was the agglomeration. If we move on to Prussian white cathodes. Prussian white cathodes are very interesting, and this is primarily due to their composition. The Prussian white cathodes consist of iron, sodium, carbon, and nitrogen. So it's a very green mix and a very cheap mix. It has a decent potential at an average of 3.1 volts, which simplifies cycling because you don't have an SCI and you don't have oxidation typically on Prussian white. It has a good capacity in theory at 170 milliamp hours per gram. However, it's a very complex structure with defects, water content, and a lot of influence of different factors during the synthesis and storage. So in paper 4, we took a look at the synthesis conditions, the defect concentration, the amount of sodium in the framework, and also how we could convert between different crystallographic structure by removing water and adding sodium and so forth. This included a lot of analysis based on XRD, SCM for the morphology, TGA for the water content, and of course cycling. My involvement in this project was a bit selfish because I wanted a good, robust cathode material for my further research into electrolytes. And by the end of paper 4, we actually had a really well-performing Prussian white material, which could be used in full cells since it was fully sodiated out of synthesis. But we also needed enough powder to actually start building a lot of cells. And therefore, it was also included that we scale up the production, and we got quite far with good properties maintained while scaling up by a factor of, I don't know, several hundred times. But having done this, I wanted to have a look at electrolytes, because electrolytes are very important. You cannot characterize an electrode material fully if you don't have an electrolyte that's good enough. And from papers 1, 2, and 3, we could see that the SCI from carbonates were not ideal. I mean, they were probably one of the best out there, but I wanted to see, is there anything better? So in paper 5, we looked at a matrix of 13 solvents. I characterized the solvents, conductivity, ionic conductivity at different concentrations, electrochemical stability in using cyclic voltammetry. And also, and this is a bit different from the normal literature, I took all the solvent-salt combinations and I cycled them in full cells. Full cells means that we don't have metallic sodium in the cell. And I wanted to see if the electrolytes had a better chance in cells without sodium metal, because sodium metal is very aggressive. And it turns out this is indeed the case. Out of 13 solvents, 11 of them cycled to some extent. And from this, we went further, and I wanted to see additives. Additives are added to electrolytes to improve the SI formation. So we selected about 5 candidates for studies with additives, and we selected several solvent mixtures to see binary solvent mixture and how that would increase or decrease the performance in a sodium-ion battery. Now, as you can see, this involved a lot of different cells, a lot of different tests. So we developed a standardized testing protocol using 3 electrode cells, which enabled us to evaluate cycling, but it also enabled us to do characteristic resistance curves on the anodes and the cathodes. The resistance measurements were done with current interruption techniques, especially ICI. And this enables us to see the impact of additives on the anodes as we cycled, and thus we could compare a lot of different systems, see if there was stable resistance, high resistance, low resistance, and also see if there was commonality between how additives acted on different solvents. As a part of this work, we also discovered the solubility of a very important salt for papers 6 and 7, namely sodium BOB. Sodium bisoxalato-borate. Now, this salt was considered insoluble in basically any solvents except water at the time. It had been characterized and synthesized, but it had never been cycled in sodium-ion batteries. And we found that in paper 5 we could dissolve a lot of sodium bob in a solvent called trimethyl phosphate. Trimethyl phosphate is a flame retardant, so it won't burn. And the analog to sodium bob is lithium bob, and that has been used to great effect in lithium-ion batteries. It's more soluble, and it also has very good film formation properties. So I wanted to see if we could combine the non-flammable nature of TMP with sodium bob. So setting out to try that in paper 6, we characterized the salt, of course, looked at the ionic conductivity, cycled some half cells, and the results were that sodium bob seemed to polarize the cells much more, but it has better capacity retention than the standard sodium hexafluorophosphate. And the conductivity, while not beating the hexafluorophosphates, it's very close, so it's quite a high ionic conductivity. However, TMP had always had issues with carbonaceous anodes, like graphite or hard carbon, so the true test came in full cells. And we saw that when we tested the two different TMP electrolytes in full cells, the sodium hexafluorophosphate was utterly a failure, and we expected that. That had been shown, but the sodium bob actually provided quite a benefit in cycling. We found by cyclic voltammetry that sodium bob reduces quite early on in the charging process, just like LiBob does. And that actually helps to screen the TMP electrolyte solvent from the anode. And you can see here in the galvanostatic charge curves the decomposition of sodium bob. Now, I wasn't entirely happy with the results. That's a really promising results, but we wanted to test if we could tweak this with additives. So we employed vinyl carbonate, vinylene carbonate, I should say, and evaluated the effect on both electrolytes. And while it improved the effectiveness of both electrolytes, it actually worked better for sodium PF6 than Na-Bob. This is most probably due to vinyl carbonate breaking down way ahead of TMP, but almost at the same time as NaBOB, which meant that we needed to use much higher concentrations of vinyl carbonate to form a good SI in sodium bob systems. But indeed, we could actually make hard carbon work with TMP due to sodium bob alone, and BC would make it quite a good cell. Now, the other strategy would be to mix electrolytes, and that's the main game of paper 7. In paper 7, we use the other solvent we found in paper 5, N2-methylpyridone, which is a good solvent, but with some toxic properties, low vapor pressure and so forth, but it's flammable. But we found it could dissolve Na-Bob, and it could dissolve a lot of it. So in terms of ionic conductivity, we could reach almost 9 millisiemens per centimeter, while TMP could only reach 5 at the best of times. So we characterize mixtures in increments of 10 volume percent, and we characterize ionic conductivity both as a function of temperature and as a function of concentration. And we also did flammability tests to see where is the limit of the mixture when the electrolyte is flammable versus non-flammable. We found that it was at 40 volume percent TMP minimum, which means we could actually mix these two electrolytes and have higher ionic conductivity, lower freezing point, etc. So this was very promising. But then when we looked at the cycling, we could see that in the first 5 cycles, adding NMP to TMP deteriorated both the initial Coulombic efficiency and the cycling durability. And even the best performing TMP was inferior to the ECDEC reference, which is a standard carbonate solvent using sodium PF6. However, as we looked further into the cycling, we could see that by cycle number 100, our mixtures and the pure TMP actually beat out the reference by quite a fair margin, which meant that we were actually performing on par with the state-of-the-art electrolyte while being non-flammable and using a very cheap and novel salt. We also found that NMP in its pure form actually performs very well at high temperature. And there is a lot to be said about NMP, but still, it's good information to have if you aim to develop high temperature electrolytes. Now, to conclude, I will say that paper 1 showed us the troubles we would have with conventional carbonates in sodium-ion battery systems, while papers 2 and 3 described the SI behavior on tin phosphide and suggested possible degradation mechanisms. Paper 4 showed a pathway to produce fully sodiated Prussian white with low defect contents in ambient pressures and low temperatures. And paper 5 was more of a mapping of the options available to full cell sodium-ion batteries. Paper 6 and 7 showed the possible use of NA-BOB to produce non-flammable electrolytes without using massive salt loadings of expensive salts. And it also showed the mixtures of NMP and TMP and how they will alter the electrochemical performance. So that brings us to the end. And I would like to acknowledge some people before I stop. And I will start with the funding agencies who have funded my research. A big thanks to them. Thanks to them, I had all the resources I needed to do my research. And I would also like to truly acknowledge my co-authors and wonderful colleagues. Without them, none of this research would have been anywhere near as good. I would like to acknowledge Christina Edström, who is the head of the Armstrong Advanced Battery Center, who has built this wonderful group. And Daniel Brandell, my second supervisor, who got me started in batteries and also helped me a lot during my PhD. I would like to direct a special thanks to my main supervisor, Reza Yunensin, because he has helped me all along the way in too many ways that I can explain here. So without his support and guidance, I couldn't have done anything you see here today. Thank you.